So now we need to get into the specifics where we maybe have a chance to get ahead of the curve and actually have some impact and put together this whole social license, if you will, around nutrients and what's happening in the Great Lakes. So that's going to be the focus of the rest of the day. Our next speaker is Dr. Merrin Macrae. Merrin is out of the University of Waterloo. She's one of the foremost researchers in Ontario on phosphorus research, in particular in tile drainage water. You heard Mark mention cover crops. I'm really intrigued. Merrin is doing some work now on cover crops. What happens to a cover crop if it freezes? Does all that phosphorus in the tissue come out? The answer is we don't know. And so what Dr. Macrae is going to try to do is paint the stage with where we're at in terms of phosphorus research and what's actually going out into the Great Lakes. Welcome, Merrin.
Okay, good morning. Thanks, Pete. First thing I'd like to do is a sound check. Can everybody at the back hear me? Yeah, we're good to go. Okay, great. Okay, so it's great to follow Mark. Certainly he's laid the stage, for, as Pete said, for some of the issues that are facing us in Ontario. And the first thing I'd like to really do at the beginning, if you can see my pictures, sorry, is really what you can see is this is my sort of my token green shot. You can see all of these green lakes. And you can also see the Gulf Zone. And the reality is, what I'd like to mention is that this is not just an Ontario issue. Okay, this is an issue in the United States, this is an issue in Manitoba, this is an issue globally. This is something everybody is looking for solutions to, and just bear that in mind, and that different types of solutions are going to vary regionally, and we have to be aware of that when we start to design management practices that are going to work. But it's absolutely a hot topic. So I guess the first question is, what is causing the algal bloom? So I'm going to talk a little bit about the science behind the issues and the science behind the solutions. So in terms of what is causing the algal blooms, I don't know if you can see this. I don't think my pointer's working either. Okay, so I don't know if you can see the picture in the top right corner, but it's a very famous picture that was done based on research that was done in the 70s by David Schindler in the experimental lakes area. And essentially, what they did is they fertilized different sides of lakes in enrichment experiments where they spiked them with fertilizers. And they used nitrogen and they used phosphorus. And what they found is that the side that they added the phosphorus to, which is that very bright green, absolutely bloomed. Okay? And so because of that, we now have a pretty keen understanding that in a lot of our large lakes and our inland lakes, that phosphorus is a big driver. You're definitely going to hear people talking about nitrogen. You're going to hear people talking about phosphorus. When we start to talk about the Gulf and the hypoxia, it's really about nitrogen. And certainly both nitrogen and phosphorus are problems, but in Lake Erie, they really feel that phosphorus is the game changer. So what's going on? The phosphorus is, you'll often hear a term called the limiting nutrient, which means phosphorus is, it's all about how much is there. If you don't have enough phosphorus, it limits algal growth. Okay, so what does the phosphorus do? The same things that you add to your plants, nitrogen, phosphorus, organic matter, these are things that help plants grow. Well, the phosphorus also fertilizes the algae. The algae behaves a bit like a plant. So when that phosphorus ends up in the lake, the algae grows and they bloom, and that's what you're seeing. Those vast swaths of green are algal blooms. And so of course this degrades our lake. You may also hear them talking about dissolved phosphorus, in particular dissolved reactive phosphorus, and total phosphorus, or sediment-bound phosphorus. Okay, so we used to be concerned about erosion, trying to keep the soil on the land, which of course we're still concerned about. But really, something that's out there now is this idea of the dissolved forms of phosphorus. And this is because that dissolved reactive form is in fact the type of phosphorus, the form of the phosphorus that is like ice cream for the algae. This is what they need. This is what they want. So we're concerned about the dissolved species, but I think it's important to realize that both dissolved and total phosphorus matter. So if you can actually, again, I don't know if you can see this or not, but if you can imagine you have a piece of sediment with phosphorus bound to it, and it can bounce off and on in terms of the water or the solution. It goes back and forth. So the reality is, although water can enter Lake Erie or any of our lakes in the sediment-bound form, that sediment can release phosphorus to the water in the dissolved form, which is then food for the algae. So it's important to realize that although dissolved phosphorus is getting a lot of press, both of these matter. Okay, so you don't want the sediment being lost either. So where is that phosphorus coming from? Well, let's start with what we call point sources, so wastewater treatment. So these are an end-of-pipe issue, okay? Now that used to be a big issue, but with emerging technologies, they've really cleaned up their act, and things are getting a lot better. So a lot of the algal problems now are coming from what's called non-point sources or diffuse sources, meaning just everywhere in the landscape. The problem with those is you can't control those. You can't just catch them at the end of a pipe because they're coming from everywhere. So examples of where that phosphorus is coming from, well, some of it is urban, we know that, but some of it is also in agriculture, and of course we're hearing in the media, lots of finger pointing at agriculture. We have to do our bit. Everybody has to do their part. So the question is, what can we in agriculture do to reduce our phosphorus losses? So in order to start to come up with creative solutions that are going to work, one thing that you have to learn is how is phosphorus actually lost from the field? So let's look at the science. So traditionally, we used to look at phosphorus as a surface runoff issue. So when water is over the surface of the soil, it's eroding that soil, pulling that off into our ditches and into our lakes. We used to be concerned about surface runoff or surface overland flow. Nobody ever worried about subsurface runoff, and we didn't worry about tile drains. But now, again, in the media, and in science, we're now learning that tile drains can actually be a pretty big source of phosphorus depending on where you are. So why are some tile drains a problem, and why are some tile drains not a problem? And how does our management impact this? So the next thing to do is look into the science again, okay, and understand what's happening with the phosphorus in your runoff. So here, I don't have access, my pointer's not going to show up. I don't think. So instead I'm just going to stand here and do some interpretive dance for you. So, okay, so imagine your field, okay? So this brown block that you can sort of see with your crop on top, you can see a tile drain at the bottom, it's lowering the water table, it's doing its job. We know that our soil phosphorus, there's some red stuff up there that I can see, is highest at the surface. And because of that, your surface runoff can be a very, very big source. But when you get percolating water that goes under the ground, which you're seeing from these white arrows, it's not really rich in phosphorus because the soil is adsorbing or sorbing, is what we use for short form, that phosphorus. It's hanging on to it. And when you have clays, in particular, and loams, they're pretty good for cleaning the phosphorus and just hanging on to it. And so because of that, we never worried about the subsurface. We never worried about tile drains. But something that we've known in the hydrology world since I was in diapers, but something that's really starting to catch on in terms of affecting water quality in agricultural systems is the concept of preferential transport or macropores. Has anybody heard those words before? Anyone? A few of you? Okay. So again, you can't see it, but essentially what we have in a lot of systems is wormholes or cracks. When clays dry and shrink and have cracks, or you have worm burrows or biopores of any sort in the soil, sometimes those things can really connect the surface to your tile drain, and they become a pathway, an open pipe vertically in the soil that routes that rich surface runoff right into the tile and right out of your system and into your ditches. So that's the science behind that. So, and the problem with this is that obviously the level of that preferential connectivity between the surface and the subsurface does vary with soil type. Obviously more into the clays, especially at the southwestern end of Lake Erie, this is where you'll see more of that shrinkage and cracking and more of that connectivity. It's not as much of an issue in loams. So because of this, tile drainage has become really, really controversial. And we know that we need tile drainage. We need to lower our water table. We're used to snowmelt in springtime. We need to get the water off of our fields. And in some areas of the world, or in some areas, of North America, such as the Great Lakes region, this is really important. So I've got a map of Ontario up on the top, and you've got the United States on the bottom, and the stuff in red that you see is where you can see so much intense tile drainage. So these people rely on the use of tile drains so that they can get crops and yields. And they're being told that tiles are the problem. And so this is really, really stressful for everybody. The bottom line is that we need BMPs that are going to work for surface runoff and subsurface runoff. Another feature, wow, you really can't see that. Okay, so, I don't know if you can see that. I can't see that. What it is a satellite image that I was able to get from NASA, and it's showing you sediment loads in March. Something that people tend to forget about is when is material moving in the environment. And we often think about, let's think about right now, the blooms are here, it's all green. It's what's people might think that it's the stuff running off of the land now. That's not necessarily the case. We know from our research that we've been doing probably, for me, over almost 20 years or more, we know that a lot of the water moving and a lot of the phosphorus in the landscape is actually moving during the snowmelt period. It's actually during the non-growing season, and how you leave your fields in the fall is really, really important to keeping phosphorus on the land. Right now, a lot of what falls, unless you get those crazy rains, but a lot of what falls just gets into the soil to support crop production. But if you're in November through March, what comes on goes out. So it's really, really important to remember that winter in Ontario is a critical period. And because of that, we need to use BMPs that are not just in the summer, but things that are going to work in the winter months as well. We have to keep things on the land in frozen and snowmelt conditions. So what are some of the current best management practices or beneficial management practices that people are using? Mark referred to no-till, okay, so no-till versus tillage. So what's the science behind that? The reality is when you go to no-till, they feel that what people did is they went to no-till to try to reduce some of that surface erosion. Okay, that would you would have more connectivity through macropores because more worm populations that would help water settle into the soil so that it could become these little white arrows, and it would keep it, it would basically help infiltrate, and it would reduce surface erosion. And this is why people went to no-till. The problem with no-till, particularly when you surface broadcast, is that they're now finding that those same preferential pathways, the wormholes that develop in no-till, are in fact connecting things to tile drains. And it's particularly a problem when you surface broadcast. So in tile drain landscapes, no-till is starting to get a bad rap. Okay? So why are people suggesting going to tillage? Well, tillage will break up those pores, mix in that phosphorus to lessen those surface concentrations. So again, if you don't till, you end up getting what they call stratification of phosphorus, where it's really accumulating at your soil surface. So if you mix it in, it more evenly distributes it throughout the soil profile, breaks up those preferential pathways, and so there's some recommendation that you should go back to tillage. The problem is we went to no-till in the first place to stop surface erosion. So which is it, right? If you till, you might increase the surface erosion. So that's a bit of a problem. Another set of best management practices that people are using, things like cover crops, riparian buffer strips, grass waterways, wascobs, basically the use of vegetation that's growing in, on top of, around your fields to try to reduce some of that phosphorus loss. So yes, they take up some of the phosphorus, but more importantly, they build soil organic matter, they hold the soil in place, the root structures keep that soil in place, they slow down that runoff so that the erosion isn't carried, it just drops out and they keep it on your field. So that's why they're encouraging people to use vegetation. The problem with the use of vegetation is that we are dominated by a winter climate in terms of our water. So what's happening to all these plants in winter when they're underneath ice or underneath standing water and they're dead? Well, first of all, they're laying down, so they're not really slowing down the flow of water. And second of all, because they die, they can release dissolved phosphorus directly into the runoff, directly into the waterways. And remember, that's ice cream for the algae. So they've become somewhat controversial. So some of the work that we've been doing is trying to figure out situations that they do and do not work in to better understand their role. Okay, so let's just really, this is the last thing I want to talk about, is strip tillage potential. So strip tillage is an interesting approach because it really has the potential to reduce phosphorus loss. Why? Well, first of all, in the areas that they're tilling, it breaks up those preferential pathways in the subsurface and it incorporates that fertilizer. And the phosphorus, of course, is only applied in those tilled zones and it's not applied on the no-till. So the tilled strips, you're not going to get the losses to surface or to subsurface and tile drainage. On the other hand, the no-till strips provide the benefit of improved soil organic matter, the vegetation and residue that might slow down that water and help basically deposit or maintain that phosphorus on the surface. And so it seems to be that it may be the best of both worlds and an innovative approach to lessening phosphorus losses from the landscape by sort of using a hybrid between these two. You have the benefit at the surface and in the subsurface, and maybe less phosphorus overall applied and less phosphorus lost. So, I mean, obviously we need some scientific studies to compare this to systems where we're not using it, but I think it has tremendous potential when you think about the physical processes that actually cause phosphorus to move off of the land. So with that, I will take questions and happy to pass on to those that are going to talk about strip tillage.
Okay, thanks very much, Merrin. Really, I think don't leave yet. We get some questions, but really, I think drives home the complexity of the issue, right? And by the way, you might sit here and say, well, why aren't they, focusing in on the number of times that London dumps raw sewage into the Thames River? And you can talk that way till you're blue in the face. But the urban people are going to continue to use their toilets, and they're looking at us first because we have less votes. Paint it any way you want, it's both. But those algal blooms in Lake Erie, when they see them, they go to the cottage, they go to the beach, they can't swim because of the algae. It's agriculture they think of first. So a really complex issue, but we have to do something about it. Questions for Merrin? So Merrin, I find it really interesting in Western Canada, right, when they look at dissolved reactive phosphorus, if they grow alfalfa, they actually are pulling more dissolved reactive phosphorus in March and April out of that alfalfa coming. So where's the fit for cover crops? You have a thought process? Like, lots of these people are thinking that cover crops are the answer, but what you just sort of telling us, I don't know that that's the answer. How's that going to come together?
Well, I think the jury's still out. I mean, the bottom line is that a lot of what we understand about cover crops in the US, they're not worried about those freeze-thaw processes. A lot of our knowledge of cover crops in areas like Western Canada or in Sweden and these areas tend to have a harsher climate than we do. They get, I mean, we all think about those Winnipeg winters, right? We don't have to deal with those. And we have a snowpack that they don't have. So their cover crops, they freeze up green and they can release phosphorus. So I think that cover crops in those types of climates are not necessarily ideal, but in our climate, we're more temperate here, and as we all know, we get a lot of snow on our fields, and snow insulates your soil. We have years of data now where often we don't see frozen soils underneath our snowpack in our fields. So I think that you can get freeze-thaw processes, but I think it's designing systems that are going to work here. I think it's understanding the science, and I think it's figuring out what species are going to work for you. But I do think they have some potential here. And even if they do release phosphorus, it may be that by building soil health and organic matter and encouraging infiltration downwards, maybe there's an indirect improvement. But I'm absolutely interested in the science, and that's exactly some of the stuff we're studying right now.
Bill?
We're closer to the Maumee River here than we are the University of Waterloo.
Yeah.
Isn't this an American problem?
I think everybody has to do their part. I don't think we can get away with pointing fingers and saying it's you guys, it's not us. I mean, I think I'm getting side glances.
Bill, you know darn well. When I talk to my sister who lives in London, and she grew up on the same farm that I did. She has a cottage at St. Joe's. When they're beach, they can't swim there because of whatever.
It's the Maumee River here.
Yeah.
Yeah,
If you even look at the image, the one that you couldn't see, you can see there's stuff in the Thames is kicking stuff into Lake St. Clair and
It's my
eventually in.
understanding the Maumee River is the biggest source.
It is the biggest source, but it doesn't it's 80%.
What's that?
It's like 80%.
80%.
But that doesn't mean we don't have to do anything.
Yeah, it doesn't absolve us, Phil, at the end of the day.
They're doing a lot of the same science. They're doing a lot of the same things. I think, from what I understand, we've got some targets in place, and Ohio has to adhere to those, just like the Thames has to adhere to them. They're quite serious with farmers south of the border as well as north. They're getting fiercely regulated, starting to get fiercely regulated there.
Yeah, if we don't step in front of it, Phil, then we'll get regulated the way they're going to get regulated. And I think that's what this whole thing is about. Yeah, they might be 80%, but that doesn't absolve us for sure. Rick, you had a question?
It's similar to Peter's. When you look at the satellite image, a lot of the green is limited to the western basin.
Yes.
And so I wonder, is Thames River as much a contributor to that problem as opposed to something happening in the eastern area like you're in?
Okay, so I'm definitely not the lake expert, but I listen and I pay attention. So I think you have a combination of a couple of things. First of all, the loads are more in those areas. The fact is that the soils, the topography, everything tends to be more conducive to letting things into the lake. And the other issue is that the lake is very shallow at that end, which means it's more vulnerable to algal blooms because it heats up even more. So it's a combination of a couple of things.
Okay, so I have one last question, Merrin, just for the group in general. Can you tell us on average how much phosphorus is lost per acre per year in Ontario into the Great Lakes system? Do you know that number?
Not off the top of my head.
Can I give it to them then?
Yeah, you go with it, and then I'll tell you what we're seeing. No, but I'll tell you what we're seeing from the sites that we've been working on, where they're employing some things like strip tillage and nutrient management and things like that. So you tell me your number first.
Yeah. So well, when I talk to Kevin Macrae, the number he typically throws out is around 0.4 pounds per acre per year, give or take. So 0.4 pounds of phosphorus per acre per year. And there's about 1,700 pounds of phosphorus in an acre in the top 6 inches. So we're losing 0.4 out of 1,700. So if you think about that, when I went to school, if I ever could have brought home a paper where I got, 1,699.6 out of 1,700, my mom would have died and gone to heaven right on the spot, right? So I mean, the amounts are quite small. That's the point I'm trying to make.
Yes.
Is that? But the problem is when you put that across whatever it is going into the Lake Erie Basin, the 2 million acres or whatever, then that 0.4 pounds becomes a big issue. Right?
Yes. Yeah, the whole thing about phosphorus is it's a limiting nutrient, which means there's not very much of it in the environment. And a little dab will do you. Like, seriously, a teeny little increase in phosphorus makes all the difference in the world. So likewise, it may only be that 0.4 number, but even if you could cut that in half, it would make a huge, huge difference. And the types of loads that we were seeing from the sites that we're working with, and Ken is one of those people, we're looking at about 0.15 kilograms per hectare, which is much, much lower. So I think that some of these approaches really have.
Very cool. Okay, we're going to have to cut it off there. Thanks, Merrin.